My name is Hector Polito, and this is Lab 5, Magnetic Braking with Faraday. For the introduction, in this experiment, we collected observational data of a magnet falling through a conductive tube of aluminum foil, modeled the magnet/tube interaction computationally, and compared the computation predictions with the observed data. And the purpose of this was to explore the interaction between a moving magnet field and a curly electric field that induces a current. The fundamental physical principles that were used in this experiment were magnetic field and force, demonstrated with Biot-Savart's law, the flux, which is demonstrated with Faraday's law, Lenz's law, and Newton's third law. The objectives for the experiment itself was to observe the average time it took for the magnet to fall through the tube, and using the computational model to calculate the magnetic field at position R, to calculate the rate of change of the magnetic flux, to use Faraday's law to calculate the force on each loop, to use Newton's third law to calculate the force exerted on the falling magnet, and to calculate the net force. The measurements that were taken during the experiment was the length of the tube, which was 0.39 meters, the mass, which is 0.02 kilograms, the width, 0.024 meters, the radius of the tube without the foil, 0.025 meters. The average measured time that we got from the experiment was 0.793 seconds, and the calculated time using the code in the model was 0.962 seconds. The calculations that were performed using the computational model were the magnetic field of a dipole using Biot-Savart's law, Faraday's law, the magnetic force, and using Newton's third law, the force on the loop being equivalent to the force on the magnet. You can see the glow script code. The first image shown here is the magnetic field, the code for the magnetic field, which shows the magnetic field of the dipole. Then you have the change in flux, and to the right you have the code that calculates the gravitational force, the magnetic force, and the net force on the magnet. Here we have the model and graph. So to the left we have the model of the tube, and to the bottom, on the bottom of the tube, you see a blue lighting indicating the magnet at the bottom of the tube. And to the right we have a velocity versus time graph showing the magnet falling through the tube. At a certain point, the velocity of the magnet levels out before falling fully through the tube. For the additional questions, what if the resistivity of the conductor were reduced as close as possible to zero? How did the dynamics of the falling magnet change? I said that the falling magnet would fall over a longer period of time due to the induced current being larger. And what if there were holes or slots that were cut into the tube? How would this affect the ring currents in your model? And I said that the current would decrease. For interpreting the simulation, the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to the clockwise current as viewed from above, and which is the counterclockwise? And how can you know? I said that the red corresponds to the clockwise and the blue corresponds to the counterclockwise. And what would happen to the dynamics of the system when you flip the magnet around? I had said that the current direction would flip.